Welcome back for our last video on our forces unit. We're going to talk about two very different topics in this video. We're going to talk about air resistance and center of mass, neither of which is a huge topic right now, but they are important enough that I do need to address them. And air resistance, that's the first one we're going to look at. We have already covered air resistance a little bit. We're going to take a slightly more in-depth look at it. A lot of the stuff we've already mentioned back in our kinematics unit, but we're going to do a bit of a deeper dive now. What is air resistance? Well, there's a lot of different names for air resistance. At its core, it is a frictional force that, just like all frictional forces, resists motion of an object if that object is moving through a fluid. By fluid, I mean either a liquid or a gas, okay? Something that is not solid, okay? We don't have air resistance for solid things, but like a liquid or a gas, something that will cause some friction on the object moving through. What does it do? How does it affect free fall? And probably I shouldn't say how does it affect free fall, since we know that free fall is defined as only gravity acting on something. But how does it affect motion would be a better phrase, perhaps. Well, in general, what it does is, since it resists motion, it does that by, it reduces velocity, or, and the maximum height something reaches, and the range that something has. In other words, the farthest it will go in the x direction. Essentially, and we're really going to look at it mainly for objects that are moving through air, okay? Not as much objects that are moving through a liquid, but we could be doing that. It causes objects to fall, if they're falling back towards the ground, at something called a terminal velocity instead of continuing to accelerate. Objects will fall at a terminal velocity instead of continuing to accelerate. Something in free fall will just accelerate and get faster and faster and faster. Something that is experiencing air resistance will eventually top out. It'll reach a speed at which it cannot fall any faster. This is a perfect time to talk about what a model is. We use models all the time in physics. Matter of fact, all the equations that you guys are learning are really best called models. They are models because they are, for the most part, approximations of what is actually happening in real life. That's what a model is. It's an approximation. It's a tool for predicting and analyzing what happens in real life. Air resistance is a perfect example of this because air resistance is so complicated, it's really, really hard to get an exact answer. Okay? Probably almost impossible. So instead, we have different models. Now, if you were to learn some of the models that engineers and like high-level physicists use, those are very, very complex. We're going to go with the most basic model. The general model of air resistance is as follows. Fd equals bv. Fd is the drag force. That's a more general term for air resistance. B is a positive constant known as the drag coefficient, and it's based on things like the object's mass, its shape, what it is moving through, etc. V is, and I have to underline this to be very clear, it is the speed of the object. It is not the velocity. Don't think of it as velocity, okay? It doesn't have a direction to it. This is simply the speed, just simply how fast something is going. Okay. Now, the whole entire thing as a whole is a vector, but we can think, at least for our approximation, our purposes, of v as being a speed. Okay. And then one little bit that I do want to talk about, or one thing that I want you to have in your head, is that one of the effects of air resistance is that air resistance causes objects to fall for longer than they rise. And there's a very good reason for this, okay? When we weren't dealing with air resistance, when we were dealing with perfect free fall, you toss something up, it comes back down, it takes the same amount of time to go up as it does to come down. You can prove this mathematically. Well, you can also prove mathematically that air resistance causes objects to take longer to fall down from a certain height back to where they started than they do to go up. And to see this, we're going to start by looking at objects that are rising and falling with enough air resistance acting on them to not be negligible. Remember that you don't have to account for air resistance unless you are specifically told to in the problem. So this is going to be an object that's rising. We're going to say the upward direction is positive. There are two forces on this object that's rising that has been thrown or kicked or launched or whatever and has air resistance acting on it. Well, there's obviously the force of gravity, Fg. There's also the air resistance force, the drag force, Fd. The net force on this object would therefore be negative Fg, since it's in the negative y direction, minus Fd equals may. I can turn both of these, I can write both these in terms of their in terms of their equations. So this would be negative mg minus bv equals may. So if we wanted to, I'm not going to write it, but if we wanted to, we could solve for ay by dividing both terms over here by m, dividing the m to the other side. We know that the force of gravity is not going to change. It's mg. The object's mass isn't changing, acceleration due to gravity isn't changing. And by the way, the acceleration here obviously is negative, since m, g, b, and v are all going to be positive quantities. This term over here, though, is interesting, because we know as objects rise up to their peak, they slow down. Since v is the speed, that means that as the object goes up and v goes down, this term goes down until it reaches the very peak where v is 0, and this may, or if we divide m to the other side, ay, is just dependent on negative mg over m, or in other words, negative g. So if you think about it, this equation, when the object is first launched or thrown or kicked or pushed or whatever, starts off very, very negative if we're solving for ay. It starts off with a very big negative number. As the object goes up and the speed gets lower, the acceleration becomes less and less negative until at the very peak, the acceleration is only equal to negative g. So think about it like this. If something's in free fall, it's always got an acceleration of negative g. If air resistance is acting on it, with that additional downward force, it actually causes it to accelerate at a greater rate, that means the object's speed will decrease very quickly, much more rapidly. So the object gets to its highest point very quickly, because it has a bigger acceleration on it than it would if it was simply in free fall. A bigger negative acceleration, I should say. Now let's look at the opposite case. Let's look at an object that is falling. An object that's falling still has the force of gravity downward on it, but it has an upward drag force this time, since, again, air resistance is a force of friction, and it works to oppose the motion of the object. In this case, here's our axis, we would have something like this. F net y equals Fd minus Fg equals may. Okay? We're still going to have a downward acceleration here, because remember, at the beginning, when this object first starts to fall, the speed is 0, so this term Fd is nothing at the beginning. We still just have an acceleration based only on the force of gravity. However, as the object starts to fall, v increases and the drag force gets bigger and bigger. That's a positive, we're treating that as a positively directed force here. So Fd gets bigger and bigger and bigger. It doesn't quite balance mg out yet, but it gets bigger and bigger. Eventually, it gets to a point where v is big enough, and the difference between these two is going to be 0, causing the acceleration to equal 0. So, once v is big enough, Fd is equal to Fg, and ay is 0 meters per second. Look what happens when we do that. bv minus mg equals may. That's now 0. We can actually solve for the speed at which this happens by bringing mg to the other side and dividing by v. V, this speed at which there's no more acceleration, and the velocity remains the same, is equal to mg, the weight, divided by b, which is that drag coefficient. And I should point out that the drag coefficient, there's a ton of variables that go into that. We're not going to take a look at it. It's enough that you know that there's just some coefficient here. So depending on the coefficient, the mass, and the acceleration due to gravity, there is a speed at which the object stops accelerating, and this is what is known as terminal velocity. So on the way down, the acceleration is always less than the acceleration in free fall. It starts off at the free fall acceleration of just g, but then as b gets bigger, or v gets bigger, the acceleration, since this term gets bigger and bigger, the acceleration decreases and decreases and decreases until it hits 0. That means the object isn't speeding up as rapidly as it was. As a matter of fact, while in free fall, there is no limit to how fast something falls, when we're looking at an object that has air resistance on it, there is a limit. This means that the object just won't travel as fast as it falls, therefore it won't cover as much distance in the same amount of time. So therefore, that is why when you have an object that has air resistance acting on it, it rises very rapidly to its peak because it slows down very rapidly, but then on its way down, it doesn't accelerate at the same rate, so it actually goes slower. Or I don't want to say it's moving it doesn't slow down, but it does not accelerate at the same rate, at the same distance fallen, at the same time fallen. It's not moving as fast, so it takes longer to fall back down than it did to go up. And that's different from when we don't include air resistance. So that's kind of interesting. Finally, I do just want to review real quick the graphs of air resistance, what the graphs look like if we're dealing with air resistance. Let me focus there so you can see it a little better. Okay, there we go. We did this in the kinematics unit, but not a bad thing to review, just so you can tell, oh, that looks like there's some air resistance going on, or that doesn't look like there's air resistance going on. The solid line will be for an object in free fall, no air resistance. The dashed line will be for an object that is experiencing significant air resistance. We'll make the 3 graphs. X versus t. V versus t, and A versus t. Now, for an object in free fall, we know that the graph of position versus time looks like this. The slope is constantly increasing, indicating that the velocity is increasing. It's because there's acceleration the whole time. Well, we just got done saying with air resistance, if an object is falling, oh, and by the way, let's make the assumptions that down is positive, and the object starts at the origin, and it falls from rest. We just got done saying that with air resistance, if something is falling, then that means that the object will eventually hit terminal velocity, in which there is no acceleration. And if there's terminal velocity, that's a constant velocity. The object can't go faster than that. Constant velocity on a position versus time graph would be shown with a constant slope. This graph never has a constant slope, but this one does. Okay, you can see there, right when it kind of tops off, we have a constant slope area here. It still was changing the slope for a little bit, but this must be it has hit constant velocity, terminal velocity. Terminal velocity. And this, therefore the slope, the velocity stops increasing. As far as the velocity versus time graph goes, if we are dealing with something in free fall, the object will continue to accelerate for forever. That acceleration is constant, so the slope of the velocity versus time graph is constant. However, for an object with air resistance acting on it, we know that the velocity eventually tops out at terminal velocity. It doesn't get any faster than that. That might look something like this. Okay, so eventually the velocity just becomes constant. Terminal velocity. The slope approaches 0. Notice it doesn't mean that the velocity is 0. The terminal velocity, it cannot be 0. Terminal velocity means the object is moving, but the slope is approaching 0. Okay, the slope, in other words, the change in velocity over time approaches zero because the velocity is constant. And then finally, for an object in free fall, the acceleration is constant. On Earth, that would be 10 meters per second squared. For an object that's experiencing air resistance, the acceleration decreases toward zero because that drag force is increasing and eventually so that it balances out the force of gravity. There's a general overview of air resistance. Let's move now to talking about center of mass, which is for right now going to be fairly conceptual. It is an idea that you have to have. As we go through the year, we'll come back to it and visit it more and more. Eventually, we'll even do a little bit mathematically with it, but we won't do a ton with it. There's a lot of different ways that you can calculate center of mass. It's a very useful concept, but in this class, we don't really take too big of a look at it. What is it? Center of mass is what I like to call the mathematical average location of mass in an object. Okay? Another way to think about it is the location where Fg acts from on average. We've been treating most objects, especially in the forces unit, as points. That's why we draw them as dots on our free body diagram. But think about this pen. Okay? Every little bit of matter and mass in this pen has a force of gravity acting on it. That would add up to a lot of little Fg vectors that all point straight down. Instead of going crazy and drawing all those, what we do is we find the center of mass, the average location of all the mass, and we say, it's not really an approximation, we say that that the force of gravity acts from this particular point. Okay? Some objects are really easy to find the center of mass in. For example, take a square. The center of mass, quite obviously, is right in the middle of the square. A lot of objects have a little bit trickier center of mass to determine. Think about like this triangle, for instance. Okay, nice equilateral triangle. All the sides are equal, or as close as I could get to it. You might think, okay, well, similar to the square, the center of mass is going to be halfway up. That's the average location. But think about it. Most of the mass of the triangle is down here. Okay, most of the mass of the triangle is down here on the lower part. Therefore, the center of mass gets pulled down a little bit, so that the center of mass is probably somewhere around here and not right at the midpoint of the height of the triangle. Okay, so you got to think about where the mass is located. A kind of interesting example is imagine that you had a donut or a ring shape. Where's the average location this time? It's actually in the center of the donut hole, if you will. Right here, there's not even mass there, but that's the average location of all the mass, which is kind of interesting. You could even have kind of like a weird shaped object, like maybe like this somehow, and that you can find a center of mass from this. Now, there's mathematical ways to do this. We are just kind of estimating. It looks like, I don't know, I didn't really draw this all that well. It looks like there's a little bit more mass kind of on the bottom part of this object than the top, maybe a little bit more on the right-hand side, so maybe the center of mass would be like over, I don't know, here for that. I should have drawn that better shape, but it is what it is. Okay? So anyways, we can predict, or we can qualitatively assess where the center of mass is by looking at the mass distribution of the object. There are ways to calculate this. We're not going to get into those now. Here's what you need to know about the center of mass right now. We need to look at this because sometimes objects or systems are what I like to call complex. They aren't things that can be generally reduced down to a point. So for complex objects or systems, and this is what we were talking about up here, the center of mass shifts to be closer to the majority of the mass. Okay? More mass will shift so that it's closer to the majority of the mass. A couple other things that you should know, just kind of general points. and we'll revisit this and talk about why this happens later on, but forces that act near an object's center of mass usually do not cause it to tip or spin as easily as forces that act further from the center of mass. Objects tend to be more stable if you put a force on them that's close to the center of mass. They won't move as easily, okay? They won't tip or spin. That's really what we're talking about. Think about like balancing something. If you're putting a force near something's center of mass and it's balanced at the center of mass, the object just won't tip or spin quite as easily. A caveat of that is that more support does tend to be needed near an object's center of mass to hold that object up or to stabilize it. Okay, so just in general, that's some quick things about the center of mass. The last thing I want to talk about is the relationship between the center of mass of an object and net force. You learned about Newton's second law. You know that Newton's second law is as follows. F net equals ma. Now, that's actually pretty close to true, but there's one other thing that we really should be adding onto the equation, and it's that the net force is equal to mass times the acceleration, not necessarily of the entire object or system, but of the center of mass, which I abbreviated COM. The net force on an object is equal to mass times the acceleration specifically of the center of mass. Why do we have to talk about this? Well, it turns out that different parts of objects can have very different accelerations. Okay? Think about, for example, a complex object. Like, think about a person running. If a person like a track sprinter, if they're starting from rest and then they're accelerating, different parts of them are accelerating very differently. I mean, if you think about it, like at certain points, like their hands are moving backwards, their different feet are moving backwards, but they themselves, the entire system, is accelerating forwards. So different parts of an object can have very different accelerations at different times. However, a net force on an object or system has a distinct relationship with that object or system's center of mass. So the individual hands and feet and whatever can have whatever acceleration that they need. But the center, if we're talking about the sprinter example, but the center of mass of the sprinter is accelerating at a rate determined by the sprinter's mass and the force that's being applied to them. And that force is being applied through the force of friction on the soles of their shoes, allowing them to propel forward. Okay, so you would treat the hands and legs and feet and arms of the sprinter as different parts of that system, but the acceleration of the center of mass of the system, which is usually about right behind the belly button or so, that's dependent on the net force and on the object or the sprinter as a whole and the mass. The hands and the feet and the legs and the arms, those are subject to their own forces, which have some And by their own forces, I mean those are parts to the system. So there's internal forces that are making those accelerate at different rates. But the center of mass's acceleration is dependent on the net force on the entire system and the mass of the entire system. So two kind of corollaries to these statements. If the object's center of mass doesn't accelerate, then there must be no net force on that object. Okay? If the object's center of mass doesn't accelerate, there must be no net force on that object. Likewise, without a net force, the center of mass can't accelerate. If there's no net force on the system as a whole, then the center of mass can't accelerate without that external net force on the system. Even if parts of the system do accelerate. So for these complex objects, different parts may be accelerating, but if the center of mass is not accelerating, then that means there is no net force on the system as a whole. Those are just some things to keep in mind about center of mass. Right now, I need you to have an idea in your head that center of mass is a thing that we can calculate. I didn't tell you how to calculate it, but we can calculate it. You have a very conceptual idea of how to find it. It exists. There's an important relationship between the acceleration of the center of mass and net force. And just in general, objects, if a force acts near an object's center of mass, it doesn't cause as much change to its motion as a force acting farther from that object's or system's center of mass. And again, without a net force, the center of mass cannot accelerate. Parts of the system can accelerate, but the center of mass of the system cannot and does not accelerate. That's it for our forces unit. I think next will be a short circular motion unit, and I will talk to you, I'll have some more videos for that. See you later. Bye.